Okay, need to lower the kind of smooth. Okay, so we have a tile supported by on three edges. And we take some measurements and we determine that two vectors here are V and W. Does anybody see where my blue chalk went? Probably lay it down someplace. Okay. So let's say that V is $30J minus 2.5K, and W is negative 30I minus 1.5K. Then we're going to calculate a normal vector, a vector perpendicular to the plane. How do you get a vector perpendicular to two vectors? Well, you take the cross product. Basic definition of the cross product. It's magnitude of this one times the magnitude of that one. Okay. And then you use the right-hand rule, cross the first one into the second one, and you get something perpendicular. So V cross W, 30J times negative 30I is negative 900. I cross J is K. So we're going to have negative 900K. And then 30J times 1.5K. J cross K is I. Okay, so 30 times negative 1.5 is negative 45I. And 30I cross 30J. Wait a minute. I think I crossed it in two different directions. Let's be careful. I cross J is K. So if we cross, okay, if we do V cross W, we get negative 900, but J cross I is negative K. That should be plus 900K. Okay. And then V cross W, K cross I, you got K, you got I, you get J. Negative 2.5 times negative 30 is plus 75. And then we have the J cross K. I'm losing track of what I'm doing because I want to look at it backwards. This cross this is plus 900K. K cross I is J. So negative 2.5. Okay, that's, except that should be J. And then 30J times negative 1.5K. J cross K is I. So that's negative 45I. 45I. And then K cross K is 0, so you get nothing from crossing this with this. I think that's the correct vector. So it's negative 45I plus 75J plus 900K. Positive in the J and K direction, negative in the I direction. Now, if you compare that with the orientation of the tile, it's you know, it started flat, but then it's tilted down this way. And if this is the J direction, it's negative in the J direction. I'm sorry, it's positive in the J direction and negative in the K direction. Okay. Which agrees with this. And then it's tilted back this way a little bit. And it gives you these two vectors. So it's tilted this way and this way. Now, what does that do to the normal vector? Okay. If this is in the normal direction, perpendicular to the plane, when I tilt it this way, it's going to have a positive component in the J direction. Then when I tilt it this way, it's going to have a negative component in the I direction. The tilt this way is a little less than the tilt that way, so the negative 45I and the 75J make perfect sense. And the K is a whole lot bigger because this thing isn't tilted very much. Okay, so there's your vector. Now we can analytically test whether this vector is really perpendicular. How can we test whether this vector is perpendicular to both V and W? Okay. So easy test for whether two vectors are perpendicular, take their dot product. It'll be zero. This is magnitude of this times magnitude of that times the cosine of the angle. Cosine of the angle is zero if and only if two vectors are perpendicular. So I'm going to use n for the normal. A lot of times smaller case, lowercase n means unit normal. This depends on the author. But v dot the normal vector, so this is the normal vector. No, 30 times 75 is 225. 225. And negative 2.5 times negative 900 is negative 225, or negative 22.5. Okay, sorry. Okay. You can easily do that. And W dot, just to be sure, 30 times 45 is 135. Negative 1.5 times negative 900 is negative 135, adds up to zero. Now you should write that out yourself, because if you don't write it out, you're not reinforcing it. And you might delude yourself into thinking that you remember, that you will remember. But if you're not writing out what you're doing explicitly, you're not reinforcing it, and you're not going to retain it as well. And you're going to have to spend a lot more time making a lower grade reviewing for the test. Okay? Reinforce it every time you use it. You find out it doesn't work for you. Okay, well, different people have different ways of learning and understanding, but that's my best recommendation. I think applies to most people. Okay. And I've been saying that for years. I've been seeing some articles that say the same thing. Of course, I'm probably cherry picking. Okay. But I think I'd notice if I saw something that said differently. Okay, well, the whole thing now is that gives you a vector perpendicular to the plane. Now, how many of you have digested the videos I posted on Tuesday? Okay. How many of you even know that I posted videos on Tuesday? They're on the assignments page. I'm not going to go over it except to use it. Okay, they're very detailed. I think very explicit, because I didn't have to stop and think. I just did it. All right. I just go over the dot product and cross product, basically, in some of the applications. One of the applications, the cross product. Well, actually, oriented toward equations of lines and equations of planes, which you will need to know they'll be assigned. Okay, I'm not going to spend a lot of time going over it today, but I will state it in this case. What's the equation of the plane? Well, I'm going to call this point X naught, Y naught, Z naught. This corner. Okay. That could be any point. Okay, I could have said, well, let's let that be the origin. I didn't want to do that. Okay. So whatever the coordinates of this point are, from whatever coordinate system you might want to set, you can put the origin any place. But the X direction will be this way, the Y direction will be this way, the Z direction. Cross product of the X direction and Y direction upward. Okay. I'm just going to leave it X naught, Y naught, Z naught. You can decide where the origin is. It might be out there in the field. It might be on the moon. There might be somewhere here in the room. Might be somewhere on the plane. Okay. What I mean by the vector X minus X naught I plus Y minus Y naught J plus Z minus Z naught K. Well, I'll draw it kind of quickly. So let this be point X, Y, Z. Then right here's my vector. That's this vector. Okay. Makes sense? Now, if X, Y, Z is on the plane, what angle does this vector make with the normal vector? Don't say it. Okay. Well, you could calculate, at least in symbols, the angle between this vector and any of these vectors. Just take the dot product, divide by the product of the magnitudes. Okay. What direction does the normal vector make with these two vectors in the plane? We just proved that it makes that the direction is zero, which it had to be because that's what happens with a cross product. You get a vector perpendicular to both vectors. Well, the two vectors define the plane. Any vector in the plane has to also be perpendicular to the normal vector. Okay? You convince yourself of that because I'm not going to give you detailed geometric proof. I'd like to, but time doesn't permit. Okay, so this dotted with the normal vector equals zero. That's the condition for this thing to be on the plane. Okay. Well, what do I get when I dot this with the normal vector? Go ahead and write it out. This is real important. It's not going to take long. You don't have to write out every detail. You look at the normal vector, you look at this vector, probably tell me what you're going to get. What's the dot product of this vector with this vector? Oh, here it is. Okay. Well, I component times the I component X minus X naught times negative 45, right? J component times J component And I'm gonna have to kind of wrap here. And then Z minus Z naught, well, the K component times the K component. This equals zero. Now, if I know X naught, Y naught, and Z naught, I can plug in the numbers and write out the equation. Suppose X naught, Y naught, Z naught is 5, 3, negative 2. There's the equation. And then if I multiply things out, that's negative 45x, negative 45x plus 75y plus 900z equals what? Well, 45 times 5 is 225. 75 times 3 is negative 225. 900 times 2 is negative 18, is 1800. So I think that comes out negative 1800. Now, I can divide through all this, at least by 5. Okay, 5 goes into everything evenly, so I'd have like negative 9x, 25y, and 180z equals negative 450. Okay, so I can reduce the numbers in the equation, but right there's a perfectly good equation. This equation represents the plane. Now, use a little more room and I don't have it, so I'm going to put this aside for a minute. Line parallel with this vector through 4, 6, negative 12. Look at the video. It just means you got 4, negative 6, 12 sitting here someplace. And you've got this vector 2i minus 3j plus 5k. And you got the line. X, Y, Z is a point that might or might not be on a line. If I take any multiple of this vector and add it to the vector representing this point, I'm going to get a point on the line. So that
I fell on I fell on oh, really? Oh, really? It's so awful.
remember what letter I used. I didn't use C in the video. Remember the letter, so I'm going to use C. That's the condition for X, Y, Z to be on the line. Where you consider the origin to maybe be here. So this vector is 4i minus 6j plus 12k. And then this vector is xi plus yj plus zk. This vector is your point is, to get the point on the line, you got to go in the direction of the vector v. If I will go twice of if I go from this point and move myself to v, I'm going to be at this point. It's going to be in the line. If I do 1.5 v, it's going to be more like here. If I do 0.1 v, it's going to be like here. That makes sense? So c is just any real number. If I take any multiple of this vector, it's going to be on the plane, on the line. If I got a point on the line, then the vector from here to that point is going to be a multiple of this vector. And that's what you just need to take away. Okay. Okay, unfortunately, I didn't record this as I was saying it. I think I said it pretty well, but you know, who knows? Okay, I started with just vector v and vector w and observed that they originate at a common point. They form the sides of a parallelogram in space. Okay, whatever the direction of v, whatever the direction of w, you got a parallelogram. The altitude of the parallelogram is the distance between parallel sides. So that from this vertex at a perpendicular down to the vector w, we do have an altitude. This is another altitude that I just drew arbitrarily, but this is an altitude. This altitude is just the opposite side of a triangle formed by the v vector and part of the w vector. So that this altitude is magnitude of v times the sine of theta. So the altitude is magnitude of v sine theta. The base is magnitude of w. So I multiply this distance by this distance, I get the area of this parallelogram. Okay, area is base times altitude, so it's this times this, and coincidentally, that's just the definition of the magnitude of v cross w. You don't care what direction it's in, you're just looking for the area. The area doesn't have a direction, although the thing can have an orientation, and we talk about that later. Okay, so there's your magnitude. Area of the base is magnitude of v cross w. Okay, now we form a parallelepiped. How do we do that? We got a vector u here. We slap that vector on each of these vertices, and we get a three-dimensional box. It's all skewed around. It's not nothing's necessarily perpendicular to anything. So we have a special name for something that's defined by three vectors. So this box is defined by the vectors v and w, which define the third vertex, fourth vertex of the parallelogram, and the vector u, which sprouts out of those four vertices. And then we complete this, by drawing edges between vertices in the obvious manner. We call this a parallelepiped. And its volume is the area of the base times its altitude. Okay, now this altitude is not the same as this altitude. I call this the altitude of the parallelogram. And we'll call that altitude P, just to distinguish it from this altitude. And I'll call this altitude PPD, parallelepiped. And I'll abbreviate parallelepiped as PPD. So how do you see the altitude of the parallelepiped? Well, it depends on how you think this thing is oriented. Where are you looking at this thing from? If you're looking at it from the right angle, from a certain angle, your V cross W vector might be here. Now remember, V cross W is perpendicular to the parallelogram down here. It's perpendicular B and W, therefore perpendicular to this parallelogram. And this parallelogram is now the base of the parallelepiped. So I should have maybe written base PPD here to be very clear that this base is not the same as this base. We'll call this base P. We'll call this base PPD. Okay. So you take the area of the base times the altitude, and you want to reconcile it. You really want to understand that. Start with the area of a rectangular solid. Okay. You take the area of the base, that's how many squares there might be in the base, 1 unit squares. Okay. And then if you come up a certain number of unit squares, then you're going to have a number of unit cubes that's equal to how far you come up times the number of squares you have in the base. Okay, think about that. Could have said that a little better, but the idea should be one you've been exposed to back in 2nd grade, filled with blocks. But the concept of volume wasn't something you could deal with. Many of you might have been able to deal with it then, but something we don't usually do in 2nd grade. Okay, well, anyhow, altitude of the parallelepiped is what? Just take this vector and project it onto this V cross W, which is perpendicular to the base of the parallelepiped, to this parallelogram here. You project this on here, and you get a vector here, which is an altitude, because it goes right to the top surface of this thing from the base, perpendicular to the base. Now, I'm asserting a lot of that. We're not going to get into the details of the geometric proof, but you really ought to think about working those out. You want to understand solid geometry just a little bit better, if you don't already. Okay, so this is the altitude of the parallelepiped. You project this vector on this vector. Now, I posted 2 videos 2 days ago, saying they didn't get these videos. It's on the assignments page. I probably should have sent an email, but there are a million details that have to be sorted out, and I didn't get to it. I apologize for that. But use those videos before you get to this, and you understand what the projection is. And it's just this vector dotted with this vector gives you magnitude of this times the magnitude of this times the cosine of the angle. Well, it's cosine of this angle, and that's going to give you magnitude of this vector times the magnitude of this vector times the cosine of the angle. If you divide that by the magnitude of this vector, it just gives you this vector times the cosine of the angle, which is the length of this vector. Now, if you digested the videos that I posted on Tuesday when we weren't here because somebody had ice on their doorstep or something, and I'm ridiculing that a little bit. I'm not ridiculing the college because of that, because somebody's ice on their doorstep and we have class and they slip and break their skull, they're going to sue us. Okay, it's the legal system that we're kind of kowtowing to there. Monday was too cold for people to start their cars, and that was a good call. The other was a legally necessary call. End of that little digression. Okay. It turns out then that the volume of parallelogram is the area of the base, which is magnitude of V cross W, times the projection, and it's actually the magnitude of the projection. No, I'm not using an arrow over the word projection. So it's a scalar projection, but it's still the absolute value of the scalar projection. Okay, so we'll do this. And I should have had the absolute value signs there. And the scalar projection of one vector on another, projection of vector A onto vector B is A dot B over magnitude of A times magnitude of B, which is writing too much, writing without thinking. We're projecting onto B. So you got to divide this by the magnitude of B, which is then magnitude of A, magnitude of B, cosine theta, divided by magnitude of B. And I'm not going to write the rest of it out. The B's go away. You just have magnitude of A times the cosine of theta. Or you take the magnitude of U times the cosine of theta, and you get this. So we're projecting U, just like projecting A, onto V cross W, just like that was B. Okay, again, digest the video, do some problems, and that'll become clear to you. Okay, now that projection, that scalar projection, I went too far with it because it's late and things got a little discombobulated when I came in. Well, that's wrong. My computer locked up through my whole preparation on it. Anyhow, here we are. Okay. Now I just erased something that I wrote before because it was not necessary. This is the scalar projection. As you know, if you've been through the video that was preceded this, the vector projection you would then multiply by the V cross V cross W vector. That's a cross. I've got it like a multiplication. You do the V cross W vector divided by its magnitude, and you get a unit vector in this direction, which gives you this vector. We don't care about this vector. We just care about its magnitude, and this is it. Okay, well, one more step. I got magnitude of V cross W here. I got magnitude of V cross W here. I just get U dot V cross W. And there's your triple product, triple dot product, or whatever you want to call it. Gives you the volume of the parallelepiped. And that's something you really want to understand because that's a really good early picture in pre-calculus. Yeah, first of all, the area of parallelogram, which is pretty straightforward. You go into 3 dimensions, it's a little bit harder to visualize, but you want to be able to visualize it, you want to be able to sketch it, and you want to be able to calculate it and show and understand why it is what it is. Okay. So assignment is, as I said, I think it's sections 2.3, 2.4, and 2.5, but do check the assignments page, which I'll double check very shortly.